Hello and welcome to Auten Math. In this edition of Auten Math, we're going to talk about imaginary and complex numbers. All right, well, what is an imaginary number? What is a complex number? Well, an imaginary number can be defined as the square root of -1. Remember, we said before that there are no square roots of negative values. Now we're saying that are real numbers. Now we're saying an imaginary number is the square root of -1. And where does this tie back into? Well, we've been talking a lot about the graphing a quadratic and a parabola. And remember that I gave you three different possibilities for a parabola. One in which it intersects the x-axis twice, one in which it intersects the x-axis once, and one in which it doesn't intersect the x-axis at all. So in this case, there are no real, in this last case, the third case, there are no real roots. There are no areas where y is going to be equal to 0. So remember, when y is equal to 0, the graph crosses the x-axis. So there are no cases where y is equal to 0. So we use the imaginary number in part to define those non-real roots for this parabola. The symbol for an imaginary number is going to be I, or a lowercase I. So when we say the square root of -3, we can rewrite that as I times the square root of 3. So if I had a number I root 3 squared, that would be the same as the square root of -3 times the square root of -3, which is equal to just -3. Now a complex number includes both real and imaginary numbers. So a real number would be 1, 2, 3, 4, or 5. An imaginary number would be the square root of a negative number. The standard form of a complex number can be written as the real number first plus the imaginary component, where a is the real number, as I mentioned, and bi is the imaginary number. Now if b does not equal 0, then a plus bi is an imaginary number. So an example would be 3 plus 4i. If a is equal to 0 and b does not equal to 0, then a plus bi is a pure imaginary number. Now we're not going to use this mathematical dialogue much, but I just want you to know the difference between a pure imaginary number and an imaginary number. All right, so let's take operations involving complex numbers. Let's talk about adding and subtracting complex numbers. When you add and subtract complex numbers, all you do is you add and subtract the real component separate from the imaginary component. So you add or subtract the real component, and then add or subtract the imaginary component. So an example would be a plus bi plus c plus di is equal to a plus c plus d plus, plus bi plus di, which is plus b plus d in parentheses I. An example would be 3 plus 4i plus 6 plus 7i. And that would be equal to 3 plus 6, or 9, plus 4i plus 7i, which is plus 11i. Now if I were to take the difference, it would be a plus bi minus c plus di. It would be a minus c, again, so distributing this negative value to the c, plus bi minus di. So it would be plus b minus di. As an example, using numbers, 3 plus 4i minus 2 plus 6i, it would be 3 minus 2, which is equal to 1, plus 4i minus plus 6i, which would be equal to negative 2i. Or I could say, in a different example, 3 minus 4i minus 2 minus 6i. That would be equal to 3 minus 2, so 3 minus 2 minus 4i minus a minus 6i. So minus 4i minus a minus 6i, which is the same as minus 4i plus 6i, which is the same as plus 2i. So now I have 3 minus 2, which is 1, plus 2i, and there's my answer, 1 plus 2i. All right, now moving on to conjugates. So we talked about conjugates of radicals in the denominator, and we said that the conjugate of a complex number, if it's just of a radical, is just the radical itself multiplied by itself. But in the case where we had a value plus a radical, it would be that value minus the radical. So remember, we did not want to have radicals in the denominator, and likewise, mathematically, we want to eliminate any complex numbers in the denominator as well. So we need to, when there is a complex number in the denominator, we need to multiply the entire expression by the denominator over itself. All right, so let's talk about conjugates again. So a conjugate of a complex number is that value when multiplied by the original complex number results in a product that is a real number. So 3 again is a real number, 3i is an imaginary number. The rules for finding, so this is number 2, the rules for finding the conjugate of a complex number are the same as those for finding the conjugate of an expression with a radical as a term. So in this case I have 3 minus root 3 as my complex number. The conjugate of 3 minus root 3 would simply be 3 plus root 3. So I said before that it's not okay to have complex numbers in the denominator, and without going through an explanation of why that is, I just say that the math gods have determined that, so leaving a result as 3 over 3 plus 3i is a no-no. Mathematically, although ultimately we can all figure out what that value is going to mean, we want to, as a final answer, rewrite the value or that expression without the complex number in the denominator. So what we're going to end up doing is multiplying both the numerator and denominator by the conjugate of the denominator, which in this case is going to be 3 minus 3i. So I multiply 3 times 3 minus 3i. In the numerator, I get 9 minus 9i. In the denominator, remember, it's just the same as the difference of 2 squares. So 3 plus 3i times 3 minus 3i is the same as a squared, which is 9, minus 3i squared. So let's think about what minus 3i squared is. It's minus 3 times the square root of negative 1 times the square root of negative 1. Well, I know that the square root of negative 1 squared is just negative 1, and I have negative 3 times negative 1. That is equal to positive 3. So I have 9 plus 3, which is equal to 12, as my denominator, and 9 minus 9i as my numerator. I can simplify this further because I have a common factor of 3, and I result in an expression 3 minus 3i over 4, which should be your final answer. Okay, so let's give some conjugate examples. I have 1 plus 5i, and my conjugate of 1 plus 5i is going to be 1 minus 5i. If I multiply those two together using FOIL, I get 1 times 1, which is 1 squared, plus 5i minus 5i. These two cancel or reduce to 0, minus 25i squared. So remember we said minus 25i squared is the same as minus 25 times the square root of negative 1 times the square root of negative 1. And minus 25 times the square root of negative 1 squared is minus 25 times minus 1, which is equal to plus 25. So now I'm left with 1 plus 25, or 26 is my answer. Okay, let's take another example. 2 minus 3i, the conjugate of which is 2 plus 3i. I multiply these two together. 2 minus 3i times 2 plus 3i, I get 2 squared plus 6i minus 9i squared. Again, minus 9i squared is the same as minus 9 times minus 1, which is equal to 9. Now I have 2 squared plus 6i minus 6i reduced to 0, 2 squared plus 9, which is equal to 13. Okay, so if I'm left with an expression 7 plus 5i over 1 minus 4i, as I mentioned before, I need to do some hair brushing just to rearrange the way my hair looks or the expression looks, but not to change the value of the expression at all. So I multiply by 1 plus 4i over 1 plus 4i. This value here is equal to just 1. So I rewrite the top term as 7 plus 5i plus 28i minus 20, which reduces to negative 13 plus 33i. And I minus 4i times I plus 4i is the same as I squared, or I'm sorry, 1 minus 4i times 1 plus 4i is the same as 1 squared minus b squared, which is 4i squared. And you have to square that entire value. So I get 1 minus 16 I squared. We know I squared is equal to negative 1. So I have 1 plus 16, and that is equal to 17. Okay, let's talk about absolute values of a complex number. The absolute value of a complex number is a non-negative real number defined by the letter z and the absolute value sign. So the absolute value of a complex number a plus bi, where I say it's equal to z, is the absolute value of that z value. And what we're doing here is we're just restating the Pythagorean theorem, because we just want to find the distance on the xy plane from the origin to the point A comma B. That's all we're doing. So I say this distance is going to be the absolute value of A plus BI. And the way that we're going to find that is the same way that we would find the hypotenuse in a right triangle. A squared plus B squared is equal to C squared. Or I can say, so A squared plus B squared is equal to C squared. Or I can say, let me just erase these squares because this really should be a B value, right? Not just C. So I have, and I don't want to cause any confusion. So this is just A, this is B, and then this is C. And A squared plus B squared is equal to C squared. Or C is equal to the square root of A squared plus B squared. So the absolute value Z is the same as the C, or the hypotenuse distance. And that's equal to the square root of A squared plus B squared. Okay, and again, we're just finding the distance of the hypotenuse, the distance from the origin to the point AB. So let's take some examples. The absolute value of the complex number 4 plus 3i is the same as the square root of 4 plus the square root of, 4 squared plus 3 squared, which is equal to the square root of 25, which is equal to 5. So again, absolute value of 4 plus 3i is equal to the square root of 4 squared plus 3 squared, which is equal to the square root of 25, which is equal to 5. The absolute value of 5 minus 12i is equal to 5 squared plus square root of 5 squared plus 12 squared, which is equal to square root of 169, which is equal to 13. So it doesn't matter really what this sign is here or in front of these values. We're just simply using the distance formula to find out what the absolute value of that complex number is. So either way, if this were plus or minus, I would still rewrite my equation as 5 squared, square root of 5 squared plus 12 squared. All right, last part. I want to talk to you about patterns that occur with exponents and imaginary numbers. So if we were to say what I is, or I to the first, that's simply as defined the square root of negative 1. I squared is the square root of negative 1 times the square root of negative 1, which is just simply negative 1. So the square root of any number squared is just that number itself. I to the third is just the square root of negative 1 times I. So I can say that it's negative I. And I to the fourth is just I squared times I squared, which is equal to negative 1 times negative 1, which is equal to 1. So I to the fourth is equal to 1. So you can see there's a pattern that's generating here. I to the fifth now is I to the fourth times I, which is just simply the square root of negative 1, or I. And then I to the sixth is I to the fourth, which is 1 times I squared, which is just negative 1. I to the third is 1 times, I to the fourth, or 1 times I to the third, which is 1 times negative I, so it's negative I. And I to the fourth is just 1 times 1, which is going to be 1. So the pattern here is every 4 exponents, every fourth exponent, in numerical order, the I value, the result of the I value with the exponent, repeats itself. So if you wanted to find the value of I to the 323rd, you divide longhand, 4 into 323. You'd get 80 with the root of 3. With the remainder of 3. So your remainder is that value that will be the reference value for the value of whatever I to that exponent is going to be. In this case, it's I to the third. I to the third would be negative I. So all you have to do is remember these 4 values, or you can just work them out as I've done to figure out what the value is of I to any exponent.